Have you ever tried to break a big number into its smaller parts? Let's take a simple one, like 15. You probably know right away that 3 times 5 equals 15. Those numbers, 3 and 5, are called its prime factors. Finding them for small numbers is a piece of cake. But what if the number was massive? I mean, a number with hundreds of digits. Suddenly, this simple school maths problem becomes one of the hardest puzzles in the world for even our most powerful supercomputers. They have to try dividing the number by every possible prime number, one by one. It's a very, very slow process. This difficulty isn't just a fun math challenge, it's the very backbone of modern internet security. Think about it. When you send a message or buy something online, your information is locked away in a digital safe. The key to this safe is made by multiplying 2 extremely large prime numbers together. For anyone to break the lock, they would have to find those original prime factors. Because this is so incredibly hard for our current computers, your secrets stay safe. It would take them thousands or even millions of years to guess the right factors. It's a brilliant system, really, using a hard math problem to create a strong digital lock. This is where things get really interesting. For decades, we have relied on this computational hardness. We built our entire digital world on the assumption that factoring large numbers is practically impossible. This method, often called RSA encryption, protects everything from your bank account details to secret government communications. It's like having a secret that is so complex you can shout the clue, the big number, to the whole world, and still nobody can figure out the answer, the prime factors. But what if a new kind of computer came along? A computer that doesn't play by the same old rules. That new kind of computer is a quantum computer. It thinks in a fundamentally different way. Instead of tackling problems one step at a time, it can explore many possibilities all at once. It uses the weird and wonderful rules of quantum mechanics, the science of atoms and tiny particles, to perform calculations that would be unthinkable for a normal or classical computer. One of the most famous things it can do is solve this factoring problem, not in millions of years, but in a matter of hours or even minutes. This changes the game completely. It means our strongest digital locks might not be so strong after all. So, how does a quantum computer crack this supposedly unbreakable code? The magic recipe is an amazing process called Shor's algorithm, invented by a brilliant mathematician named Peter Shor in 1994. Think of it as a clever plan that uses both a regular computer and a quantum computer, each doing what it does best. The algorithm is a 2-part act. The first part is classical, involving some setup and checking the final answer. The second and most crucial part is purely quantum. This is where the real magic happens, where we find a secret pattern that quickly leads us to the factors. Let's break down the plan. The classical computer starts the process. It picks a random number and does a quick check to make sure it doesn't share any factors with the big number we want to break. This is a simple step. Then it sets up a special mathematical function. The goal of the quantum computer isn't to guess the factors directly. Instead, its job is to find the period of this function. A period is just a fancy word for how long it takes for a repeating pattern to start over again. Imagine a spinning carousel. Its period is the time it takes to make one full circle and return to the start. Finding this period is the key. For a classical computer, finding the period of the function related to a huge number is just as hard as factoring it in the first place. It would have to calculate the function's value for one input after another, waiting for the pattern to repeat, which could take an eternity. But for a quantum computer, this is the easy part. It uses a powerful tool called the Quantum Fourier Transform. This tool is designed to spot repeating patterns or frequencies in a huge amount of data all at once. It's like having a superpower that lets you listen to a massive crowd of people and instantly pick out a single repeating melody. Once the quantum computer finds this secret period, it hands the number back to the classical computer. The classical computer then does some more simple maths using this period. With a bit of luck, this calculation will reveal the prime factors of our original big number. Sometimes the algorithm doesn't work on the first try. Maybe the random number we chose wasn't a good one, or the period it found was not useful. But that's okay. We can just run the algorithm again with a new random number. Because it runs so fast, a few retries are no big deal. All right, let's put on our lab coats and try this out. Our mission is to factor the number n equals 15. First, the classical part. We need to pick a random number, let's call it a. That is less than 15. Let's try a equals 7. We do a quick check to see if 15 and 7 share any factors other than 1. The greatest common divisor, or GCD, of 15 and 7 is 1. Perfect. This means 7 is a good choice to start with. Now we set up our special function, f of x equals 7 to the power of x mod 15. The mod 15 part just means we find the remainder when 7 to the power of x is divided by 15. It keeps the numbers from getting too big. Now we need to find the period of this function. This is the quantum computer's job. Let's see the pattern. For x equals 0, 7 to the 0, mod 15 equals 1. For x equals 1, 7 to the 1 mod 15 equals 7. For x equals 2, 7 squared is 49, and 49 mod 15 equals 4. For x equals 3, 7 cubed is 343, and 343 mod 15 equals 13. For x equals 4, 7 to the 4th is 2401, and 2401 mod 15 equals 1. Aha! The pattern of remainders is 1, 7, 4, 13, and then it repeats. The sequence starts over at x equals 4. So the period, which we call r, is 4. A quantum computer would find this r very quickly using the Quantum Fourier Transform. Now we hand this period, r equals 4, back to our classical computer for the final steps. The first check is to make sure the period is an even number. Is 4 even? Yes, it is. If it were odd, we would have to go back and pick a new a. Next, we do a little more maths. We calculate 7 to the power of r divided by 2 plus 1 and 7 to the power of r divided by 2 minus 1. In our case, r divided by 2 is 2, so we get 7 squared plus 1 equals 49 plus 1 equals 50. 7 squared minus 1 equals 49 minus 1 equals 48. These are our two special numbers. We are almost at the finish line. Can you feel it? The excitement is building. The very last step is to find the greatest common divisor of each of these numbers with our original number n equals 15. First, GCD of 50 and 15. The biggest number that divides into both 50 and 15 is 5. Second, GCD of 48 and 15. The biggest number that divides into both 48 and 15 is 3. And there you have it. The factors of 15 are 3 and 5. We did it. Shor's algorithm has successfully used a quantum trick to find the hidden factors. It turned a very hard problem into a series of simple, manageable steps. Consider this problem solved. So we factored 15. That might not seem like a big deal, but the method we used is revolutionary. For a classical computer, factoring a 200-digit number is a near impossible task that could take longer than the age of the universe. For a quantum computer running Shor's algorithm, it's a solvable puzzle. The bigger the number, the more spectacular the quantum computer's speed advantage becomes. This isn't just a small improvement, it's an exponential leap forward. It's like comparing a person walking to a spaceship traveling at the speed of light. They are not in the same league. This incredible power has a huge impact on our digital world, especially for cryptography. The RSA encryption that protects so much of our online lives is built on the belief that factoring is hard. Shor's algorithm proves that for a quantum computer, it isn't. This means that once we build a large, stable quantum computer, many of our current security systems will become obsolete. They could be broken, and the secrets they protect could be revealed. This is a serious concern for governments, banks, and anyone who uses the internet. The locks we all rely on could suddenly be opened. But don't panic just yet. Building a quantum computer powerful enough to break modern encryption is an enormous engineering challenge. Today's quantum computers are still small and prone to errors. However, scientists and engineers all over the world are working tirelessly to overcome these hurdles. At the same time, a new field called post-quantum cryptography is emerging. Experts are busy designing new types of encryption that will be safe from both classical and quantum computers. It's a race against time to create new quantum-proof locks before someone builds a quantum key. In the end, Shor's algorithm is more than just a clever piece of maths. It was a wake-up call. It showed us the incredible potential of quantum computing and forced us to rethink the very foundations of digital security. It unveiled a new kind of power, one that will undoubtedly reshape our technological future. It reminds us that, in science, what seems impossible today might just be waiting for a brilliant new idea to unlock it tomorrow. The quantum revolution has begun, and it's going to be a wild ride. Science rules.